Good morning, chemistry students. Today we're going to be taking the next section of our notes online because I'm going to be out of the class for one of the days. So I'm starting on this screen, this slide, just in case you didn't already get it. Most classes talked about this, but I think a couple didn't. So we're going to be using Celsius and Kelvin. They're pretty easy to convert. If you wanted to change Celsius into Kelvin, you just add 273. If you wanted to change Celsius into Kelvin into Celsius, you subtract 273. So it's all about that 273, and you have an example of that on your worksheet. All right, a couple of the things of measurement we just need to talk about really quick is heat. So we talked about temperature as a measure of the heat transfer. So heat itself is really energy in transit between two systems. We talk about a temperature difference, that's how we're measuring it. Heat is also energy, right? We talk about heat energy. When we think of particle energy, it's kinetic, it's the energy of motion. So that's why I have this little picture down here. Solid would have the least kinetic energy, moving the least, they're tightly packed, they're kind of vibrating. Liquid, we usually have a little bit more energy, and then gas would have the highest amount of kinetic energy. Now gases might not always feel as hot, but because they are moving the fastest, they actually have the most heat energy. So we're talking about heat, we're really talking about the movement of the particles. Transfer of heat, it always goes from places of high energy or high temperature to areas of low temperature. That's why your hot coffee or hot chocolate will cool off quickly, because it's going to release its heat into the atmosphere. Things always move from high to low. Our SI unit, Standard International Unit for heat, is the joule, Joule. We abbreviate it with this big J. And then another common unit that we'll see often is the calorie. We abbreviate that CAL. 1 calorie is equal to 4.18 joules. And it's important to realize this calorie is the same kind of calorie that we see on the back of our food labels, except actually the calorie on the back of our food labels is a kilocalorie. So that means that if it's a kilocalorie, let's put a K for kilo, 1 kilocalorie is equal to 1,000 calories. So they just abbreviate it, that's calorie. They abbreviate it calories on your food labels just to make it easy, but 1 kilocalorie is actually what a calorie is on your food label. So it's on the same scale, just a little bit different. Okay, so that's heat energy. We'll get to a whole chapter on heat, but just as long as you're aware that when we see a joule or a calorie, we're talking about heat energy. Next, really quickly, specific gravity. We use this as a comparison of densities for different substances. So a lot of times if we're looking at a solution that has multiple liquids in it, we are going to use density to figure out specific gravity. So it's a type, we use water as a reference, and water's density is 1 gram per milliliter, makes it a nice reference. Specific gravity has no units because we're comparing two densities. So to figure out the specific gravity of a substance, usually it's a mixture of solutions. You take the density of the substance and the density of water and compare the two. Okay. One of the places this is used really often is in brewing. My husband's a home brewer, and to figure out how much alcohol is in his beer that he makes at home, he has to use what's called a hydrometer. And it's a glass tool that you put in, it floats in the solution, and it tells you how dense is that mixture that you made. So he takes a reading at the beginning, right? When he first brews it, there's no alcohol in it, it would just be sugar right now. And then after it ferments and some of that sugar turns into alcohol, then he takes another density, another specific gravity, and that tells him how much alcohol is formed. Because if you remember from our distillation lab, alcohol is much less dense than water or oil when we took a look at that. So just as long as you know, this is just for your reference, copy it in your notes. Again, with this video, you can pause, write the stuff down, and then press play when you're ready to keep going. All right, so then we're going to move on from these measurements. Roman numeral 2, we're going to talk about measurement. So we did the uncertainty in measurement, or the significant digits, today in class. So you got introduced to some of the ideas of significant digits. So we're going to move on and give you a little bit more background information. We've talked about two types of data. Now, we've mentioned these before. Qualitative data is descriptive, non-numeric. Think quality. So it tells us about maybe the color or the texture, but it doesn't tell us anything about the numbers. So it it describes a quality about the substance. Quantity gives a specific number, a definite form. So it's associated with how much. So like how much of that do you have? What's the temperature of that? Okay. So quantitative would always be numbers, and qualitative is going to describe a quality. So color, texture, smell could be a quality. Okay. Whether or not it formed a precipitate, that would be a quality you'd recognize. Okay. A measurement can be no more reliable than the instrument you use. And we've mentioned this before. We don't do any of our measuring in beakers because their graduations are so far apart. We'd have to estimate in between those lines. But a graduated cylinder is much better. It has many more lines, so you can be more sure of your measurement. You guys saw that today in the packet. We talked about accuracy and precision before, and when I was reading through some of your reflections from that chapter, some of you were still a little bit confused. So we go over this in this chapter again. Accuracy denotes the nearness of a measurement to an accepted value. So it's how close are you to the actual known value. We can calculate our accuracy by experimental error. So we take the experimental value, whatever we go into the lab and we come up with. So if you think about the density lab we did last class, we would put your experimental density in here. Then we'd take the actual, so for whatever metal you thought it was. Most of you guys said aluminum. So the actual would be the 2.7. The 2.7, we divide it by the 2.7, and we get experimental error. See how close were you to the accepted value. Oh, and then we times by hundreds of percentage. Then precision was the other side of quality in your numbers or quantitative analysis. So precision is just concerned with reproducibility. So sometimes scientists don't always know what the right answer is. So all we have is reproducibility. Now I've shown you these bullseyes before, so if you already have them in your notes, you don't have to write them down again. But remember, precision is I can get the same answer multiple times. You guys were looking for that in your density data last time. You wanted to see, were all my densities the same? Now that didn't mean your density was correct all the time, but if they're the same, usually they are correct if you're getting the same numbers over multiple trials. So this bullseye would show poor accuracy, good precision here. Good accuracy because we're in the bullseye, we're in the accepted value, and good precision because we're reproducible. Okay. Couple notes about accuracy and precision. Accuracy depends on the quality and the calibration of the measuring device. So depending on what you use, like you wouldn't have gotten very good measurements if you used a beaker for your density, where you dumped your metal in and then the water was in between the lines. But most of you used graduated cylinders, hopefully all of you did, and you got better data for your volume. Then precision is limited by the skill of the experimenter. So in that density lab, if you had been really careless when you added your metal pieces to the graduated cylinder, so if you dropped them from a high distance, you may have noticed that some of that water splashed out of the graduated cylinder or splashed onto the side of the graduated cylinder. That throws off your data. That's probably why all your measurements were not exactly the same. Okay, so precision is really limited by how good of an experimenter are you, okay, and the number of lines you have on your device, the number of graduations. All right, so we'll be talking more about precision and accuracy when we do our lab for this, our big lab for this chapter. And I just wanted to touch then on uncertainty in measurement. You've seen this already. This is what our packet was about today, and they used an example of a ruler. I'm going to use an example of a graduated cylinder. So when we take a look, it says, when taking a volume measurement for a liquid always measures from the bottom of the meniscus. So one of the things about water, it's actually attracted to the glass because of its polarity. So you may have noticed that when you have water, you get this curvature inside the glass. You always want to do it on eye level, get eye level with your graduated cylinder, and you want to measure from the bottom of the meniscus. So here we get a nice clear line. You can see it's in between the lines. So when the meniscus is between graduations, that's the lines, we must estimate the final digit. So if I look here, it's 20, and if I look, each line is worth 1 milliliter. So 1, 2, 3, 4, 5. So I know for sure that it's at least 21, and then I'm going to estimate between the digits. So that estimation might come out something like this. If I had 4 different students take this measurement, they can all be sure of the 21, but the last digit, because this is an estimated digit, might be a little bit different. okay, because between the lines, so one might say it's 0.4, one might say 0.5, 0.6, 0.7, right? So all I know is that it's at least 21 milliliters. And you should take a guess at that middle one. If it was exactly on the line, you should use a 0. If it's perfectly on the line, you'd put 21.0, because that would tell me that yes, it's definitely on the line. So the certain digits in these measurements are the 21. So we have this 21, the first two digits, because they're not estimated. We know that it's past those lines. Then the uncertain digits would be the third digit, okay? And we could not guess past the third digit because we're already guessing at the third digit, so it wouldn't be appropriate to put, 21.55 because we're already guessing at the 0.5, so we wouldn't add an extra number that we don't know. So with this certainty and uncertainty in measurement, we only take a guess at the last digit. And then when I read a number, I'm going to say whatever this last digit is, I can assume that it's estimated. All right? And we'll do one more quick slide. When taking a measurement, we report all the certain digits plus one uncertain digit. So that's basically what I just said. So we're looking at a burette here. Okay? Now the way a burette is read is you go, it's how much has been delivered. So 39. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that each line is going to be worth 0.1. So it'd be 39.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 40. So now, how do you report this measurement? Okay, so I'd like you to kind of think about it, jot it down in your notes. What do you think? Then a measurement is only as accurate as the instrument you're using. So this is a pretty precise measurement. We can be sure that it's at least 39. We know it's 39.1, and it's 39.2, so we'd say 39.2, and we could guess at that final digit. In all measurements, there is a degree of uncertainty, and to account for this uncertainty, we use significant digits, also called significant figures. So, before wrapping up this video, here I know for sure it's 39 milliliters, and then 0.2, these are my certain digits. Now I'm going to take a guess at this last one. I'm going to say 0.4. Okay, so this one, this 0.4, is my one uncertain digit. Okay, so when I look at this number, 39.24, that tells me that, oh, whoever took this measurement guessed at that last one. All right, so that's your introduction to sig figs. We'll talk more about these in class next time. You do have an assignment today. It's just on going over those basics of measurement. All right, see you in class.